Okay, before we dive into today's lecture, I want to quickly go over the course projects. So here are the final list of projects. All of these, each of these projects are going to be supported by a mentor, as I mentioned before. And the topics here are listed, and I will be posting the project descriptions by the end of the day today. I have all the descriptions in except for one, so we're just waiting on that. And if it doesn't come right away, I'll still post everything so that folks will have a chance to start reading through them. The project topics are a range of basically applied energy policies for a variety of different and topics. So for example, CAFE standards, those are the corporate average fuel economy standards, looking at improving fuel efficiency for vehicles. And so there's a lot going on with that right now. That's pretty interesting, including some pretty big political battles. So those are the types of things that you'll learn about as you read through the project descriptions. In terms of next steps, everyone will need to read through all the project descriptions, and then for any ones that you're particularly interested in, take some time to do some of the additional reading. There are resources attached to basically all of the project descriptions, and links for either articles or papers to read. So once you've done that, then by the end of the week, please fill out the Google form listed here. I will also post this on Canvas. If you don't fill this out, then you're going to be assigned at random to a group. Unless you don't care about that, please make sure to fill out this Google form. I'm going to be then messaging each group on Canvas. Okay, I see a question. I'm going to get to that in just a second. So I'm going to message all the individuals for your assignment in terms of the topic and your other fellow group members, as well as contacts for your mentor. So basically, once you get assigned your mentor, you're not gonna meet with them in person. There's no in-person meetings for this class. You'll have to schedule a meeting either through Skype or Zoom or whatever client, doesn't really matter. And you'll have a quick virtual sit down to work through the project description, ask any questions, and they'll give you sort of a rough idea and some guidance in terms of what to think about and what to work on for the project. So you'll have basically over the course of next week to do that. Okay, so hopefully that clarifies that question. Unless there are any other questions about the course project, I'm gonna continue on to the main topic of today. All right, so over the last couple lectures, we've covered some of the introductory sort of thought processes and methods about energy conversion and things to think about. And now, starting this week, for the next couple of weeks, we're going to be talking about fuels and technology in a little bit more detail. And this is an energy policy class, and so there are lots of sort of associated policies with any particular fuel or any particular technology. And some of those may pop up here and there during the lectures, but just keep in mind that we'll be doing a much sort of deeper dive into specific policies regarding fuels and technologies sort of later on in the class. So all of this is sort of getting your baseline sort of familiar with the particular sort of energy source and how it's used, so that we can talk a little bit more comprehensively about policy down the line. Okay, so some things to think about. What are fossil fuels? How are they used today? We're going to cover a lot about resource availability and adequacy. So, how much of the supply do we actually have? Are we running out? And then thinking about environmental impacts and how they affect climate change. Okay, so starting off, thinking about coal and natural gas. So both of these are forms of fossil fuels. Okay, so what are fossil fuels? They are formed by decomposition of dead organisms and through exposure to heat and pressure from the Earth's crust. The chemistry of this organic matter sort of reforms into basically these fossil fuels. And they really are sort of fossil fuels, right? They're coming from former live organic matter. And the whole point of fossil fuels is that they contain high percentages of carbon, which makes them really amenable to combustion or burning. The most common types of fossil fuels are crude oil, which you derive petroleum, or petroleum is derived from crude oil, natural gas, and coal. Okay, and so you can think of these three as basically your solid fossil fuel, which is coal, your sort of liquid fossil fuel, which is your crude oil, and then your gaseous fossil fuel, which is natural gas. Okay, so we're not going to be talking about petroleum today. That'll be covered in next lecture. We're going to be mainly focused on coal and natural gas. So the primary reason for the distinction actually is it isn't anything particular about the division of the fossil fuel from a sort of chemistry perspective. It's that natural gas and coal is primarily used for stationary sources. So thinking about like power plants or industrial processes, whereas petroleum, right, gasoline, that's mainly being used in transportation. So that's kind of the dividing point. I guess we're, okay, here's a question here. Which fuel is the most preferable energy? Well, that's kind of an interesting question. There isn't, among the sort of three types, right, we can use them for a fairly wide variety of different uses. And so there isn't necessarily one that is more or less preferable. We'll talk about, the strengths and the cons of using a particular fuel source. And there definitely are some that maybe we would prefer for certain reasons, but there's nothing inherently sort of better about one particular type of fuel source than another, at least sort of holistically. If we were talking about like environmental reasons, for example, then you may prefer natural gas to coal, but we'll cover that. With regards to coal, and actually with regards to basically all of these things, the chemistry associated with a fossil fuel, as you can imagine, isn't necessarily uniform. Probably the one that is sort of the most if I were just to say natural gas, which is methane, CH4, yeah, so that's probably the most simple one, but it's not as though you get like pure streams of natural gas sort of extracted from the ground. They're mixed in with lots of other things. And so, yeah, you could purify natural gas, but it takes, time, energy, resources, money to do that. And so, even natural gas that's being combusted in the power plant, or natural gas coming to you if you're using your gas stove, it's not going to be always 100% pure. And so even with something as simple as natural gas, it's not necessarily kind of a uniform product. But definitely that's really true for crude oil and for coal. So crude oil, you can have, light crude, heavy crude, and the composition of what's in the crude oil can differ. So, you typically extract some amount of gasoline from crude oil, but the amount that you extract can depend on the type of crude oil. And for coal, right, you can imagine that not all coal is exactly the same. As a solid, that you've got sort of really weird, complex molecular structures, and that can have sort of lower and higher content of specific types of atoms, particularly things like nitrogen and sulfur. And so that can affect its grade and composition. So the three general ones that we talk about are lignite, bituminous, and anthracite. And that's sort of in order on the slide. L is for the lowest grade, bituminous is mid-grade, and anthracite is high grade. And I'll talk about what that means in a little bit. Okay. So the chemistry of coal and natural gas, the solids are typically the most complex, and you can think about why that is, right? For it to be a solid, you need sort of these long and large hydrocarbon chains, and the more complex and the longer and more structure there is in the molecule, the more likely it is to be, a liquid than a gas, and more likely to be a solid than a liquid. And so this is, on the left-hand side, a sort of small example of a typical sort of coal structure. You have lots of these hydrocarbon rings, and you can see that there are embedded with them, for example, these sulfur atoms within the molecule, which means that when I combust it, right, you're going to get lots of interesting sort of side products. It's not just like purely carbon and hydrogen in sort of the ideal combustion that we had been talking about before. And then sort of as a sort of really drastically different example, natural gas on the right is fairly simple in terms of its molecular structure. It's just methane, so CH4, so carbon bonded to 4 hydrogen atoms. But as I was mentioning before, you can have lots of impurities when we're extracting this, and these include things like CO2, hydrogen sulfide. You can have water vapor, some oils. So all of these things will be included in the extraction process, and natural gas will definitely get refined and processed, but it won't get to 100% purity. So you're always going to have some kind of side products when you combust natural gas, similar to what you would get in coal. And we'll discuss some of those emissions later on in this lecture. Okay. And so depending on the chemical composition, the energy density and energy content of coal can be pretty different. Okay, and even for natural gas, because of the impurities associated with it, you could have kind of a range of energy content. And so you'll probably remember in the reference slides before that we basically gave this one number for like gigajoules per ton of coal. Okay, and you know that's kind of the number that you would use on the homeworks and use for sort of a generalized look at the energy content of coal. But in reality, right, you actually have a fairly wide range of energy content. In fact, you know, the worst sort of coal, lignite over here, can have only basically half the energy, less than half the energy content of some of your higher grade types of coal. And so, you know, these chemistries are you know, determined by the energy densities are determined by the chemical composition of the coal, which fall into these categories here. So again, the way I like to think of it as L for lignite, which is your low grade, and then your B grade and A grade. So from low to high in terms of energy content. Again, the higher the energy content, typically it means the higher ratio of carbon, and then less sort of presence of impurities such as sulfur, such as nitrogen, and so on. Natural gas, generally, we're going to say about 1,000 BTU per cubic feet. But again, it can have a range depending on how much impurities are contained within the gas. Okay, how do we get the fuel? Okay, so for coal mining, this is kind of a basic schematic high-level diagram of the different types of mining that you can do. Essentially, you'll have in something like this mountain, doesn't always have to be in a mountain, you'll have these coal beds that are located basically in these horizontal striations underground. And so you can have these mountaintop mines where they're sort of working away the surface and getting at the coal. You can have coal beds in what are called drift mines, where they just sort of go horizontally straight through the land. You can have slope mines where you go sort of diagonally down to get at a coal bed reserve. Or you can have shaft mines where you sort of drill straight down until you hit one of the coal beds, and then you sort of work your way horizontally to extract the coal. And so it's a fairly straightforward process, very labor intensive, but this is essentially how you go about extracting the resource from the ground to use to provide electricity. It also has some fairly significant localized environmental consequences. So even sort of independent of burning the coal, you can have land use change affected via the mining process. So this is an example of strip mining, where they'll sort of clear the land to get at resources underneath the sort of natural ecosystem. Ends up looking something like this. And then typically they'll sort of fill in the area back with dirt and gravel afterwards. So I don't actually have that picture, but this is sort of what it looks like after it's been strip mined, before it's filled in. So, you know, important to think about some of the consequences of land use change, aside from, you know, a lot of what I'll talk about later in terms of environmental impacts are associated with the combustion of the fuel, but there are other impacts as well. Okay. for natural gas resources and extraction, this is a picture of a drill that will extract natural gas. And so they go into, a conventional sort of pocket of gas that's oftentimes sort of mixed in with some liquid like water, and you extract that, purify the natural gas, and then sort of ship it away. There are alternative ways of extracting natural gas resources, such as from shale, which we'll talk about a little bit later. But conventionally, you kind of just drill straight into your resource, your conventional gas resource, suck it up to extract your natural gas. Okay. So that's covers kind of the basics of what it is, what coal and natural gas is, and how it's extracted. So now we're going to talk a little bit about the consumption of these resources and how their resource availability is sort of worldwide. So I dug up this slide from an older set of lectures for when this class used to be taught. And here you can see a diagram of the global primary energy consumption. And so I think we've looked at some charts like this before. But I guess one of the points is that look specifically at this endpoint, which is 2010. And you can see generally the trends of crude oil, which has sort of skyrocketed since the advent of our personal transportation, and then natural gas in sort of third place, and coal in second place here. And so this slide is a more updated consumption figure, and okay, it's not quite the same because the last one is globally, whereas this one is specific to the United States. But one of the big trends that you'll notice is that where natural gas and coal were sort of pretty close with each other over the last decade or so, natural gas has sort of shot up, and coal has decreased quite a bit. And there are some pretty specific reasons as to why that happens that we'll talk about a little bit later in this lecture. But just know that this is the type of trend that we're seeing sort of worldwide: a decline in coal and an increase in natural gas. And when it comes to environmental impacts, we'll see that this has led to actually a really big decrease in emissions. If you remember carefully from a previous lecture, I had talked about how natural gas has about half the emissions for the same amount of energy as coal, and so that's one of the big reasons why natural gas has played such a big role in reducing electricity sector emissions. Okay. So we've definitely looked at some of these Sankey diagrams before. So thinking about a lot of the end services in terms of mobility, industry, heating and cooling for buildings, and other services. When we look at basically how most of that is fulfilled worldwide, again, there's a fairly sort of low proportion of things like renewables and nuclear energy, right? So that constitutes a little bit less than 10% total. And when we think about fossil fuels, coal, gas, oil, these three together are producing something like 80%, a little more than 80% of all, or providing about 80% of all the energy that we need. Sort of thinking qualitatively about fossil fuels, one of the big reasons why they're really hard to replace is that they're just really a nice convenient fuel, right? It has sort of really high energy density. That is to say, the carbon content and the energy we can extract from combustion sort of just drastically outweighs, the amount of energy from renewable resources on sort of like a energy density basis, right? So there's a ton of sunlight out there, but you'd have to capture a sort of large proportion of it to compare to, a relatively small quantity of oil, gas, or coal. And so that's one of the fundamental difficulties in going about trying to replace these energy sources. Actually, this particular chart, so this is the same thing, but for the United States, similar type of story, right? Natural gas, coal, petroleum, and again, same story again, where this coal used to be at 30, 40% a decade ago, is now down to about 10%. So I had shown a version of this graph in a previous lecture, but actually since then, Lawrence Livermore National Lab actually released the 2019 energy consumption. So this figure is kind of an update of the previous one. And you can see the sort of slight changes in the primary energy provision across all of these different fuel types. And again, to reiterate that there is a good deal of rejected energy. In other words, a lot of this is actually heat loss associated with the combustion of these fuels. And again, this is something we'll talk about a little bit more in detail today. Yeah, and so again, this sort of underscores this idea about whether or not renewables are growing fast enough. When we look at the growth of any of the technologies, by far the ones that are growing the most over the last couple decades are renewables. And so the change, the annual change in terms of amount of energy worldwide, you can see here. And the diffusion of the renewable power technologies by share percentage worldwide can be seen here as well. And so growth of these things is definitely happening really quickly. And there's just this question of like, are we growing fast enough to sort of alleviate the pressures from climate change mitigation, or to assist in climate change mitigation and alleviate pressures in raising global temperatures, alleviating sea level rise, ocean acidification, all of those factors. All right. So there is an ongoing debate about whether we will run out of fossil fuels and what the transition is going to look like. Okay, and so this is a nice little diagram of something called the Hubbard curve, which is actually originated from thinking specifically about oil resources, but also is applied to other natural resources such as coal and natural gas. And so we'll think a little bit more carefully about this. But what this diagram is essentially showing is that we are consuming fossil fuels roughly at this rate per year, so 10 to the 14th, right? So this is what we call sort of a back the envelope sort of order of magnitude estimation, right? And so, you know, our rate of consumption will change a little bit from year to year, and then there are trends where it's sort of increasing in consumption over time, right? You can think about as energy needs increase or as population increases, we're just sort of consuming more energy. And so despite all of that, sort of when we're thinking about, you know, to the tens digit, we're essentially using about 10 to the 14th kilowatt hours per year. And so when we think about the consumption, the rate of consumption, you know, we can only consume that as long as there is stuff available. And so how much is available? Well, there's a lot of debate about that, and we'll see some of that debate in just a moment. But at a high level, right, it's not going to last us more than, you know, 500 to 1,000 years, according to this particular chart. And when we think about the span of humanity from you know, tens of thousands of years, then this is definitely not a resource that we can rely on forever. And so however this sort of shape is, or however this distribution is shaped, you know, even if it goes out a little bit farther, sort of at the high levels of orders of magnitude, it's definitely still a limited resource considering how long we think, you know, human civilization may be happening. Okay. So let's think about the fuels as sort of limited resources. So these fossil resources can be defined in terms of energy reserves, which are depleted over time. And so you can do that in sort of different units, right? We can think of like the total amount of energy, or you can think about the barrels of oil, or you can think about like tons of coal, or cubic meters of natural gas. Some unit that shows basically the stock of how much fuel there is. And so we can say, by having that unit, we can say what our reserves are measured in. In contrast, renewable energies, which are by definition renewable, are defined sort of differently, because you have these energy flows. And so it's sort of like you have a constant replenished supply. And so when we talk about renewables, we usually talk about the amount of energy that they can produce over the course of a year, or the energy flow. So for sunlight, that might be something like the amount of energy on one patch of land over the course of a year. So that would be kilowatt hours per year per meter squared. So we think about fossil energy resources as sort of like a bank account, whereas renewable energy is analogous to like cash flow. In this parentheses, I actually have this thing where I'm saying fossil energy is like a bank account of ancient solar energy. And the reason for that, right, is that fossil energy really is just converted solar energy, if you think about it. All the organic material that compose the fossils used to come from plants and animals, right, which derive their energy from the sun. Ultimately, it all comes down through photosynthesis. It's just been condensed and compressed and put together under heat and pressure for a long period of time. Okay, so some more sort of formal definitions of energy resources. So a resource is whether it's everything, whether it's discovered or undiscovered, or whether it's recoverable or not. Okay, and so what does that mean? So we can have a pretty good sense of like how much like coal, how much oil, how much natural gas there is that exists sort of under the surface of the earth, whether we've sort of directly discovered it, which means like geologists have gone in and sort of identified the specific resource, and also looked at exactly how much is sort of contained in a particular resource area. So even if it's undiscovered, we have kind of a rough sense of how much resource there is. And then there is a question of whether or not it's recoverable. And so that means, oh, we know that it's there, but we don't necessarily have the technology to extract it. Or it could even be like an economic thing where it's like, we know that it's there, we can get it, but it's not worth it for us to recover it because it's too expensive. Okay, and so what does that mean? So you can imagine that maybe I discover an oil resource in my backyard, and it turns out there's a bunch of this stuff available, but it's going to cost me more money to extract that resource than I can sell it for, right? Because there's like a going price for, say, like gasoline based off of how much it costs other people to extract it. And so on the basis of economics, resources may be unrecoverable because it just doesn't make sense to do it based on the price, and that can be one of the reasons why recoverable resources can change over time, because the prices are changing over time. And then there are the unrecoverable resources where we don't have the technology to sort of extract it or maybe purify it. And so a subset of the resource is recoverable. And then of the recoverable resource, you have located it, but you haven't used it yet. And so those are what we call reserves. You have proved reserves, probable reserves, possible reserves, and so those are associated with probabilities. It's actually the reverse. So P95 is proved, P50 is probable, P5 is possible, and that refers to the probability that the resource can be used essentially as a reserve. You have the yet to find, which are the part of the resource that basically isn't located yet. And then you have the ultimately recoverable resources, which is the original endowment reserves. Cumulative production refers to everything that has basically already been extracted. So the total ultimate recoverable resources is equal to what you've already extracted and produced, plus the reserves, plus the yet to find. And this diagram can maybe help to demonstrate that. And so the cumulative production to date, that's everything you've already gotten. You've got your proved reserves. And so that is stuff that you've located but haven't used yet. Economically recoverable resources are stuff that that's there, but that aren't worth sort of recovering. And then technically, economically recoverable resources are things that that you know are there and are worth recovering. And then there's a subset of stuff that's technically recoverable, but maybe not economic. And so this is stuff that's not yet worth recovering because the pricing is to extract it is, or the cost to extract it is too expensive. And then this is all the rest of it, which is stuff that you can't actually extract. And so as you go from sort of right to left in this diagram, there is less certainty in the availability and measurement of the resource. The reserves themselves can change over time, right? So we can get, and there's a couple of reasons for this. You can get better information, and it can help identify previously unrecognized reservoirs and pools, or pay zones within an existing field. The recovery efficiency may improve. So say your process used to be able to get, 50 out of 100 units of the fossil fuel, and you say you go up by 55, or you go up to 55, an increase of 10%. So now you can extract 55 for every 100 parts. In this case, you are increasing your reserve by 10% because now the efficiency is extracting essentially more of the fuel. And then, as I had mentioned, the recoverable volumes can be revised based on economic or regulatory conditions. And so maybe it says, a regulation says, okay, if you drill this way, it's way too damaging to the environment, so you're not allowed to do this anymore. And so that can change a reserve number. Or if the price of a particular fuel, maybe it drops, right? And then it no longer makes it economic to extract a particular resource, then the reserve can change. Recently, growth of reserves has been volumetrically more important, which means that what we're seeing in existing fields, those are usually the things that are changing the reserve numbers rather than discovering new fields. So reserve growth between 1996 and January 2004 was outpacing new discoveries 3-to-1. So there are some estimates that a lot of the existing oil in developed fields kind of remains unextracted, because there's more than what we thought. We just can't get to it with current technology. Okay, I see a question. What do you mean by growth of reserves? Okay, so if I go back to, when I go back to here, this proved reserves here is often changing, right? So our proven reserves are based off of what's economic and technical. And so your total amount of reserves, according to this definition, resources that have been located but not used. So all of this quantity can be either sort of shrinking or growing based off of what we see in terms of what what cumulatively is discovered And so that could be, you discover like a underground cavern of a particular resource, and you measure that, and then subsequent sort of like more detailed measurements, you might find that it's bigger than you thought, right? So that affects the reserve. And then, whether or not you can make it cheaper to extract or more efficient to extract, or have technologies that would extract things that you previously couldn't extract, all of that will affect the reserves as well. Okay, so then to give you a rough idea of how much is sort of left remaining, you can do the ratio between the reserves and the annual production. In other words, it's like, here's your bank account, here's how much we use every year, when is your bank account going to run out, right? So you just do reserves divided by production. Okay, and so what do these ratios look like? So in 2014, there's, or in 2015, there was a statistical review. They do this every year. The BP, which is one of the big oil companies, released this report where they estimate what the RP ratio is. In other words, how long they think they can you can last with the reserves compared to how much is being used. And they do this for all three of your general fossil fuel resources, for oil, natural gas, and for coal. And so here are essentially the ranges of numbers, right? And so all of oil and natural gas is basically under 100 years, whereas coal can vary from 100 years. There's this estimate from former Soviet Union. I don't know why they do it quite like this. I think this is, they're using older sort of European geographies, and these range from 100 years up to a couple hundred years. And so basically, at the rate that we use energy today, unless we shift the way that we use the energy, or switch to a different source of energy, we'll run out within basically this general timeline.
Sorry, is that before the use of fracking in the US?
Yeah, so this particular RP ratio does include some of the fracking, and so the natural gas numbers actually used to be a little bit, it used to be, well, actually, I'm not sure what the annual the RP ratio would look like, but the reserves used to be different, and the production used to be different, but they're different in directions that would make them go, make the RP ratio not sort of unidirectional, right? Because you have more reserves, but you also are using more. So I don't know what the ratio looks like.
Thanks.
Yeah. Yeah, exactly. So the question, so if the column is higher, it lasts for a longer time. Exactly. So basically, this is the number of years that the resource would last. Okay, how much energy is consumed by humans? I've shown a picture of this figure before. Maybe it might be slightly different, but generally this is what the primary energy content for each different fuel type is consumed by humans, except oh, sorry, that's the blue is the annual global energy consumption by humans, and then the rest of these are all sort of resources. So there are slightly different metrics here. Again, for all of the renewables, that is the annual amount that's available, whereas these ones are the oil, gas, coal, uranium are essentially the rough total reserve available for each of these resources. And so you can see sort of roughly, if how much of the global energy, how many sort of, how many of these volumes it would take to consume through all of your sort of fossil fuel resources, right? And the box down here is the total solar energy across the whole world for 1 year. So it's not as though we'd be able to take advantage of all of this solar energy, but on the other hand, we don't actually need to, right? We only need kind of a small fraction of the total solar energy. Okay, and so this is part of what Facundo was alluding to, and we'll talk a little bit more about this in a second. These are natural gas reserves sort of changing over time. And so it's increased by about 50% over the last 20 years or so. And you can see the shift actually. We're going to talk about fracking in a little bit and how that's changed things. North America has increased their amount. So these are percentages of share, but the actual quantity of proven reserves has increased actually quite a bit. Maybe not proportionally, because everyone is doing what the US is doing, but the reserves themselves have grown quite a bit. Similar story for coal power and coal fuel resources, except that actually reserves have been a lot more sort of relatively flat compared to natural gas. These are actually, not to scale, right? It's actually increased a little bit, but not very much. And the proportions have not shifted much either. You can see that in comparison to the last one, where the vast majority of natural gas resources are from the Middle East, right? Maybe a little bit less than half. The most of the resources are not in the Middle East for reserves of coal. US, Europe, and Asia has most of the reserves of coal, and actually the United States and Australia probably have the best quality of coal. And so when we think about going back to the types of coal, anthracite, bituminous, and lignite, we are sort of well positioned in terms of having one of the higher densities of high quality coal, which is why there was formerly quite a bit of coal use in the United States. Okay, so let's take a quick break here. We've sort of finished talking about reserves and availability. We're gonna touch into this pretty unique thing that happened with the United States and since throughout the rest of the world. known as the natural gas shale revolution. Um, so let's convene for, let's say, 5 minutes and come back at 1:10 to finish out the rest of the lecture. And in the meantime, if anyone has any questions while you're stretching, let me know. Okay, it's been 5 minutes, so let's get rolling again. Sort of as I was mentioning, there's been this pretty interesting shale revolution that happened just in the last 10 years or so. Okay, this has been actually a pretty large transformative event in our energy system, and I guess as an average consumer, unless you're working in the energy field, you probably haven't heard so much about this. You get your electricity, you pay your bills, and that's it. And it's like, okay, what does it really matter if my energy is coming from coal or natural gas, right? But it's had lots of sort of large ripple effects, both in how the electricity grid works, the economics, the price that people are paying for electricity, how markets are working, and even on things that we do care about, like environmental outcomes. So basically what happened was this dude in Texas figured out a way to extract fossil fuel resources from shale. And so this had been stuff that this was the example I'm giving about, with reserves being known but technologically not able to be extracted, right? There is a striation of material called shale deep underground that has this sort of network of fractures that contain a lot of fossil fuel resources, but we weren't able to extract them before. And what this one guy did, he figured out how to basically extract that resource. And the way you do that is, so you drill straight down into the shale, and then you have these horizontal drills that go out horizontally, and you pump this really high pressure fluid into the hole, which basically opens up the fractures, and a lot of the gas and sometimes even oil in the shale will flow back through the pipe, and they basically extract it, right? Okay, we're not going to get too much into the mechanical engineering and chemical engineering of how this happens. They're pumping specific types of fluids to do this. And basically that opened up this whole new world of resources. And that dude who invented this made his company really, really rich. Actually, that guy himself didn't end up getting any money, unfortunately. But now, if we look in the United States, we had been a net importer of oil and gas for a pretty long time. And once the shale energy and extraction was made available, then a lot of these untapped resources were then sort of taken advantage of. So there's a couple big famous shale resources. So the one actually near where I was in grad school is called the Marcellus Shale. And that was actually, when I was in grad school, was the time where the shale fracking boom was just getting sort of started. And so there are a lot of students who were doing research on that. There's the Bakken Shale reserves up in Montana, North Dakota. And that has become sort of famous for. If you ever travel through there, you'll see these things called man camps, where basically there's these miners who go from location to location, basically taking advantage of the available resource. And they live in these like pop-up cities, which are pretty crazy because they kind of just come up overnight. And then the Barnett Shale in Texas. So all these resources has led to a really big increase in the use of natural gas, which has dropped prices for natural gas down. And what that ends up doing is it makes it more competitive than something like coal, which is one of the main reasons why coal has been decreasing, is because it's uneconomic relative to natural gas. One of the ironic things about this is when we think about fossil fuel resources in the context of climate change, people don't like it, right? It's like burning fossil fuels, which results in emissions. Let's see. I see a quick question. Was fracking discovered in 2011? I think the technology was first developed. I want to say, I have in my, I'll check this, but I have in my mind that it was in 2007 or 2008 was when the technology was invented to do the extraction. But of course, it took a couple years for it to sort of build up and all of that. And so it wasn't like a 1 year thing where everything came into place and everyone started drilling. It was, the discovery of this technology, refinement, growth of the resource, and then more people putting more resources into figuring out what the shale resource availability was. Okay, I totally lost my train of thought here. But anyways, oh yeah. So with regards to climate change, one of the ironic things is even though a lot of people uniformly think of fossil fuels as bad for climate change, and this isn't me advocating for natural gas or anything. The one thing that I would say about this is that beyond any sort of climate policy or any sort of thing that we've done to try and mitigate our emissions, the development of fracking has reduced CO2 emissions to a far greater extent than any policy, because we've been replacing so much coal with natural gas. So that's kind of an interesting thing to keep in mind. And that's not to discount a lot of the negative aspects of fracking. So this chart on the right was one of the sort of more nice diagrams that I could find, that I could dig up to show how fracking works. But you'll also notice that this is a pretty environmentally I don't want to say biased, but it's definitely one of the it's a diagram that points out a lot of the environmental flaws of fracking. It's not just a diagram of how fracking works, right? So they're showing a lot of the possible drawbacks, things like leaking of the fluid in fracking into water tables. Methane gas escaping during the mining process. So if you'll remember, methane itself is 30 times worse than CO2. And so leakages of methane, not only during mining, but also in processing and in transportation, is a really big deal. And actually the guy who made this diagram, his name is Bob Howarth. He is a professor at Cornell University. That guy was one of the first ones to publish a paper on the environmental damages of fracking and sort of the drawbacks of using natural gas. And I'm happy to actually I'll dig up that paper and include it in the reading if anyone's interested. a lot of folks think that he's a little bit extreme. Actually, it's this field isn't actually even his expertise. He's actually I think he's like a soil ecologist. Um, that having been said, him sort of shining the spotlight on fracking and the environmental consequences of fracking led to a whole lot of people sort of responding to his work and looking at this more carefully. And yeah, all of this sort of drama was sort of playing out when I was in grad school. So I remember a lot of my former professors talking about it and having lots of controversy about it. So yeah, so shining the light on this is I think a really important contribution that he made. Yeah, okay, I see Facundo making a comment, fracking requires a massive amount of water. Exactly, and that's actually one of the other big ones that's actually, I'm kind of surprised they don't have more about this on this diagram. You pump a lot of this water and they extract it, and the water that's used in fracking, it's a tremendous amount of water because you're basically having to displace this very large volumes of area that you're drilling into. And then what happens with the water afterwards? Well, that water is crazy polluted because I was talking about a lot of those impurities, right, that are associated with natural gas and with oil. All of that stuff, volatile organic compounds, pretty toxic chemicals kind of just sit in the water. And you can imagine that if they can get away with it, they'd probably just dump it, right? And a lot of it right now is kind of just sitting in these pools next to the fracking sites, and they don't really know how to deal with it. And so that's a really big problem, and you definitely don't want stuff like that getting into the water table. That would be really bad. In fact, you guys can YouTube this. There are actually videos of stuff. What happens when you get some of these materials leaking into the water table is that there are videos of people who can light the water running out of their faucet on fire, which is mind-blowing, right? That you can light water on fire. Yeah, so it's not good if that happens. And then one of the other side effects of this thing is that in Oklahoma, for example, in the Woodford Shale, they weren't doing a good job with replacing the water with material, and they ended up getting like I don't remember the exact number, but they were getting hundreds of earthquakes, minor earthquakes, as a result of essentially doing the fracking. So that's also one thing to keep in mind, is that you can cause some earthquakes. Okay, so it's increased natural gas reserves. So this is what Facundo was mentioning before, right? So these are measured after the fracking technology became available, and you can see that the proven shale reserve resources, or sorry, not the proved reserves, but the shale resources that haven't been taken advantage of yet, increased very suddenly. And we can also see across the different shale resources, these are some of the ones I was mentioning, right? The Marcellus Shale, the Barnett, and the Bakken. So all of these guys have tremendously increased since that technology was first developed. And so basically from the order of less than 5 billion cubic feet per day to above 60 billion cubic feet per day. That is a lot of natural gas, right? And so what has that meant for economics? We can see the average price of coal has been sort of relatively flat, whereas the average natural gas, so this is a spot price at a particular hub, has sort of really decreased since the 2000s. And note that I think that these are actually in nominal nominal prices, and so all of these prices would actually be a lot higher in sort of today's dollar. So basically, natural gas prices have basically plunged and made them more competitive than coal. When we get to the lecture about the electricity grid, we'll see more specifically what sort of implications that this has. And you can see that going back to that original slide from earlier, this increase in natural gas is corresponding to this decrease in coal. And again, that's sort of a replacement of electricity production in the electricity sector with natural gas. Okay, yeah, what's the technical difference between shale gas and regular gas? Is it just descriptive of the source? Exactly. So we call, more typically they call the regular gas conventional gas, and shale gas is unconventional gas because the typical methods are different. But at the end of the day, natural gas is natural gas, so it's just methane. It's just that conventional gas is easier to get and has sort of lower environmental impacts compared to shale gas. But shale gas, there is a lot of available resource, and since the technology was discovered to be able to extract that really economically, it's become sort of this unique thing, and sort of that's why we're calling it shale gas, so that we can distinguish between the regular and this one. But the fuel itself is no different. Okay. So now let's talk about how we actually produce power from coal and natural gas. So these are process diagrams for basically the supply process. So once you extract the coal, it gets transported over to a coal plant, and you essentially grind it up into fine dust, and that allows for the coal to be combusted more efficiently, right? So you can think about what would happen if you took fuel like a drum of gasoline or combustible fluid, and you were to throw a match in it, right? The top of it would burn, but all the liquid below the surface would essentially be sitting there waiting until the top layer sort of fully combusted, right? And so imagine what would happen conversely if you aerosolized it, right? You increase the surface area, the combustion is able to take place faster and more efficiently. So it's the same principle for coal, right? For a solid, if you grind it up into dust, it's essentially like aerosolizing your fuel and allowing for faster, more complete combustion. So that's sort of all of this stuff. It's basically going through these various filters and crushers to make sure that you are at the sort of coarseness that you want for combusting the fuel. Natural gas is pretty straightforward. So once you get out of the well, it gets refined and separated into oil, water, and other stuff. Some of it gets vented and flared. And then through the processing plant, you remove a lot of the byproducts and impurities. and then it gets compressed and eventually sent to your end use. And so the main one that we're going to be talking about is for producing electricity, right? And so this is kind of the supply chain for natural gas, which is a little bit different. Because with the coal, a lot of the refinements, and by refinement, I really mean just processing by reducing into finer particulates happens at the coal plant, whereas natural gas happens at a sort of processing plant. Okay, so before we talk about sort of a layout of like a power plant, I need to give a quick refresher about producing electricity. So hopefully this is a bit of a review for you from physics, but essentially what I'm showing here is a generator. And so a generator is something that converts mechanical energy into electrical power. So you have two parts, a rotating part and a stationary part. And so those are called the rotor and the stator. And so the principle that this works on, if you remember from physics, is if you move a magnet through a coil of wires, you will induce an electric field. And that is what's generating electricity. And so basically, this particular configuration is a way of taking advantage of that principle. In this case, you're actually holding the magnet fixed and you're spinning a wire, and that's the thing that's creating electricity. Okay, I have a little, I don't know if you can see in the camera, this little generator here. So this you may have seen before. It's basically a little hand crank, and so I can spin it, and that'll light up this little light bulb. And so this is exactly this process is exactly what's being shown here. I'm basically spinning this hand crank, which is moving a wire through a fixed magnet to generate electricity, and that electricity is powering the light here. So the whole name of the game for generating electricity, and like the vast majority of electricity, is produced by getting something to spin. Okay, so all of our translation of chemical energy into electricity happens by changing our chemical energy through combustion to spin an object. And the spinning of that object is the thing that will make the electricity. And as a quick note before I go on, this object here that I have in my hand, which is also the thing that you're seeing here, it's a generator, but it's also a motor. Okay. This will be kind of relevant later on when we're talking about transportation. But a motor is the same thing as a generator, but it's operating in reverse, right? So if I were to send an electric current through through the wire, I can induce a magnetic field to get it to spin. So so essentially what that would mean is like if I could connect the two electrodes to something that produces electricity, if I could produce enough electricity, I could actually get my hand crank to spin on its own, right? And so that's operating in reverse. Generators and motors are the same thing, going in different directions. Okay, so how does this relate to our discussion about coal and natural gas? Well, the way that we extract energy from the chemical compound is through mechanical energy by spinning a turbine. Okay, and so essentially what this does is it extracts energy from fluid flow and converts it into work. Almost all electricity on Earth, the vast majority of electricity from Earth, whether we're talking about coal or natural gas or even burning oil power plants or nuclear power plants or even wind turbines, all of that is getting from spinning something. Okay, and so common types include all of these things I just talked about: steam turbines, gas turbines, water turbines, and wind turbines. You don't need to know too many sort of technical details. This isn't a mechanical engineering course about how it works. These are, for example, two different types of turbines. You've got an impulse turbine and a reaction turbine. Essentially, the design of this is you've got either some kind of gas or steam, which, okay, is technically a gas, moving through a turbine. So these green parts are fixed, okay? So these don't move, and they're shaped in a way that pushes the air in a particular direction. So the air is in blue, and it moves through here, and it gets shot in this trajectory because it moves through these fixed green things, these fixed nozzles. And then it hits this red curved portion, which are able to rotate. And so these will move in this direction, and we'll see a picture of a turbine in just a second. And so the air bounces off this and moves forward and causes this portion of the turbine to rotate. Okay, and so this is kind of the side. This is kind of a slice of the turbine through its cross section, and then this is a sideways view of the turbine. In our reaction turbine, it's a similar type of process. You've got these fixed nozzles, these are the stators, and then the red portion, which is the rotors, which are moving. And so the gas gets pushed in this direction. It goes and then it rotates the rotors and then moves outwards like this. Okay, so high level, you're basically getting air to move through the turbine quickly. You can imagine that. So actually, if I go back here really quickly, that when the air gets sent through here and it hits the rotor and then moves forward, it's still got some kind of, it still has some energy, right? And so it's going to move through progressive sequences of these things to continue capturing the energy. And so you have multiple stages of these turbine blades going through here. They allow for, essentially, the reason why the diameter and circumference of the turbine sort of changes like this is that it allows for drops in pressure while still capturing the energy. So you can imagine that if the blades are still really big, after it's lost energy, it's going to have a hard time spinning it. And so you proportionally decrease some of the size to allow for the drop in pressure and the decrease in speed. So this is a picture of what's called a modern steam turbine. So what you send through this turbine is hot water, steam, essentially. Okay, so this is an example of a steam plant. And so this is specifically a coal steam plant. So in the process one, which I had discussed before, this is all the processing, pre-processing, where you grind up the coal into fine particulate dust. And you send that into a furnace, okay? And so in the furnace, you are combusting your fuel, your aerosolized coal, and some of the fuel product can be sort of recycled because you're not basically able to combust everything at once, and so you want to be as efficient as possible. You have solid material from combustion that accumulates in the bottom in a pit. So at the bottom of the furnace, you'll get stuff like slag, which are impurities that turn into solids. You also get impurities associated with the combustion, right? So CO2, but also things like nitrous oxide, sulfur oxides, particulate matter, so on and so forth. And that goes through this chimney stack. And I'll come back to that in a second. You then have 2 loops of water, essentially. So this one going into the turbine and generator and coming out of the turbine and generator is a closed loop. And the water in this closed loop gets heated up from the combustion process, it turns into steam, and it's sent through the turbine. And so you can imagine that this is where most of the energy is lost, right? So when I combust something in a furnace, if all of the heat energy could go into the water and heat up the water into steam and send that steam through the turbine in a perfectly efficient manner, then you are able to capture most of the energy associated with the combustion. But also, you can imagine that the gases coming out of the exhaust here are pretty hot, which means some of that heat is lost to the heat content leaving the chimney stack. The furnace itself, while it's insulated, it can't be perfectly insulated, and so you're heating up that whole environment. So all of that heat loss that's not getting transferred into the water is like energy that was contained in the coal, but is not being translated into energy of heating up the water. And so when we talk about the energy efficiency of coal going to electricity, this is where a lot of it is lost, and that's why we can't have sort of perfectly efficient processes. Okay, so you get this hot steam passing through the turbine, which spins the turbine, right? And again, keyword is spinning here, which allows you to take advantage of a generator. And so that generator takes that spinning and turns it into electricity. Okay, great. And so then you've got some water that's condensed out of the turbine. So all of that steam passes through, gets cooled down, and then passed back into the furnace. Okay, and so the steam or water that comes out of the turbine basically has it's not like cold once it comes out of the turbine, right? The turbine is only able to take advantage of some proportion of that heat, and so that's another source of the efficiency loss, is that you're not necessarily able to extract all of the heat energy that you would want out of the water. Although technically it's a closed system, so you are sort of getting the proper like delta. And one of the things you'll notice here is that the condenser, the way that the water is sort of cooled before it gets back into the steam, into the furnace to heat up, it's in a separate loop. Okay, and so why is that? Well, the water that you want going through the turbine, you want it to be really pure, right? If you have any impurities going into the turbine, eventually that's going to build up and you need more maintenance and more cleaning. And so what they've done here is to create a separate loop where now you can take water that cools down the stuff coming out of the turbine and gets sent back through. And so all of the stuff coming out of the cooling tower, that might be coming from like a river nearby. And so you can use that water, even though it's really impure, to cool down the closed cycle water loop. And then you send that back out, and that some of it is going back into the stream as sort of warmer water, and then a lot of it is going through this cooling tower and evaporating as water vapor. So these things can actually have a pretty significant amount of water use as well. There are two sort of chimneys when you go to a coal plant. And one of them is this longer, much higher chimney stack, and one of them is a cooling tower. And the stuff coming out of the lower to the ground one is just water vapor, no big deal. There might be some stuff, impurities in the water vapor associated with what was flowing in, but for the most part, it's just water. Let's see. Okay, quick question. What energy resources do we use to create the steam? Can it be any kind? So this particular example is showing coal combustion, but as you can imagine, you can heat up water by combusting other types of fuels as well. So commonly for steam, other types of steam plants are nuclear plants, which use nuclear radiation and these control rods in water to heat it up and turn it into steam. Natural gas, which we'll talk about in a second, is a little bit different, but can also do this sort of thing. Okay, and then in the chimney stack, it's pretty different. It's much higher because oftentimes they have these filters, and also because the higher up it is, the more it'll disperse in the air before it reaches sort of ground level. And so there are regulations that lead to the development of filters and heights for chimney stacks. And we'll get to that much later on in the class when we talk about regulation and policies that have affected the design and operation of these plants. But anyways, that's kind of a high-level overview of what you might see in a typical coal plant. So hopefully now you guys can have a nice little picture in your head about how I'm going from coal to electricity. Natural gas is a little bit different. They use not steam turbines, they use gas turbines. And so this actually doesn't have any water components associated with it, or steam, right? So what you do is you have this turbine, which has three portions. It's got a compressor upstream, which is this part on the left here. In the downstream part, which is on the right over here, it has a turbine, which is basically the opposite of the compressor. And then you've got a combustion chamber between 1 and 2. Okay, so what's happening here? So you use a compressor to essentially push air through and compress it to high pressure. And then you combust it, okay? And so in here, natural gas, the methane that's passed through my compressor is combusted and it's forced out the back. And then you have a really sort of hot stream of fast-moving gases, or pretty fast-moving gases. And that gets ejected out of the turbine, and you are spinning the turbine, right? Which means that now you can produce electricity. And actually, these turbines are really common. There are lots of designs, but for example, a gas turbine that you would use for electricity generation is essentially the same design as the one powering an aircraft. So you could literally take a turbine off of an airplane, a gas turbine, and stick it into a power plant, and it would work no problem. It would work exactly as you sort of need it to. You probably wouldn't want to do the reverse, where you take a gas turbine out of a power plant and stick it on an airplane, because there are probably some things that you would need to do to insulate the turbine and have the proper power rating and everything to operate an airplane. But for the most part, they're basically the same thing. So basically, again, push gas through, blow it up, and then send it out. And that spins the turbine. And so this is why I was saying with natural gas, it's actually a little bit different. There's no steam or water involved. So when we talk about a steam turbine, the efficiencies of these things get up to, you know, about 35% or so. Modern gas turbines are 30% to 35%, really sort of on the high end. A lot of the gas turbines are a little bit more efficient. You're probably talking more more along the lines of 35 to 40% efficient. So in terms of energy content in the fuel to extracting it. But actually, the thing about natural gas is that you can actually take more advantage of this system. And so there are some plants that have just this thing that you see here, which is just a regular old combustion turbine. But one thing you might notice, if you were paying close attention to what I was saying, is that what comes out of the other end of that is really, really hot gases. Okay, and so we can take advantage of that heat, and we can combine that with a steam turbine. And so this is combining so in a natural gas cycle, we call that a Brayton cycle, and we call the steam turbine a Rankine cycle. This is something that you might learn about in a more sort of mechanical engineering class, but you can actually combine these things. Okay, and so here I would have my typical combustion turbine, my gas turbine, where I compress my air, send in the gas, combust it, and then you have hot exhaust gases. And then you have a closed loop system where cold water is heated up by the exhaust gas from the gas turbine and then sent through the steam turbine. So when we think about efficiencies, it's like I lose a whole bunch of energy to heat coming out of the gas turbine. Well, now let's try and recover some of that heat and send it through a steam turbine. So you use those hot gases, heat it up to heat water up to steam, send it through the steam turbine, and then cool it down. And so in this case, we can actually take advantage of the heat in gas turbines and combine it. And with this, a combined cycle plant, which is what we call a natural gas plant with both a gas turbine and a steam turbine, the efficiencies can reach as high as 60%. That looks something like this. This is a typical natural gas plant. You'll have like a gas turbine with your generator, and then that's connected to a steam turbine as well. So you've got both components. This is a diagram of resources in the United States. We can see different fuel resources. So you've got most of your coal plants. Okay, so the size of the power plant is the size is how big the circle is, and then the color of the dot indicates the fuel type. So blue is coal, and purple is natural gas. One of the things you'll notice is that there's a lot more coal in the Midwest and in the East Coast. There aren't so many coal plants on the West Coast, and in fact, in California, we're actually not even allowed to operate any coal plants. So you won't see any blue dots in California, although technically we do import some from other states like Nevada. And then natural gas is in purple, and that has really sort of skyrocketed over the last couple of years. And we'll revisit this chart later when we talk about other resources. You know, you can see all the wind in the middle of the country in gray, and pink for solar, a lot of that on the two coasts. Okay, so the last thing that we'll talk about today are environmental impacts associated with the use of these fossil fuels. We've talked about combustion before. So this is the generic chemical formula for natural gas. It's pretty straightforward. Ideal combustion would look something like this: methane plus oxygen, and you just get CO2 and water. But as I mentioned before, there are a lot of impurities. You can't get a pure natural gas stream, and so that's going to result in a lot of these other compounds. Most of these are pollutants. Some of these are greenhouse gases. Coal combustion is way less straightforward. If you remember that molecule that I showed way at the beginning of lecture, those vary a lot from coal to coal, so there isn't really a chemical formula that we use from here. But a lot of the impurities includes both solids and gases. So you'll have like fly ash, flue gas, bottom ash, boiler slag. And then for gases is everything that we see up here, but also with much higher concentrations of sulfur. You get very small amounts of sulfur with methane, but pretty high amounts in coal, which is pretty problematic. It can cause acid rain and other pollution effects. And it also contains like weird metals, so you can get mercury, arsenic, other heavy metals. So coal combustion is definitely not ideal for thinking about pollution. It's got lots and lots of side products. There's been a lot of regulation to help clean this up, and we'll talk about what sort of difference that's made, and what sorts of technologies have been implemented as a result of regulation later on, once we get to some of the more specific policies. So other environmental effects, so thinking about CO2 emissions. So this, I've talked about this a couple times, but here we can show maybe a little bit more clearly. So I think the big sort of thing to take away from this is so natural gas and coal, in terms of like energy consumption, it's almost kind of like a one-to-one replacement. So coal energy consumption has decreased by some amount, and natural gas has increased by some amount, relatively similar to the quantities that are displaced. On the other hand, because the emissions associated per unit of energy are so much lower for natural gas, so that the number to sort of roughly have this in your head, I gave some reference slides in previous lectures, so you can always look those up, but the numbers I generally keep in my head are you get about 1 ton of CO2 per megawatt hour of coal, or megawatt hour of electricity made from coal, whereas you get about half that, so about 500 kilograms of CO2 per megawatt hour of electricity produced from electricity. So here, even though it's a one-to-one consumption, coal emissions has decreased by about 700 million tons annually, and actually even more than that now. Whereas natural gas emissions has increased by about half of that, 300 million annually. Okay, so the last slide that, or two more slides, the last thing that we'll talk about is CCS, which is known as carbon sequestration. And this is a concept that is being explored. This isn't really something that's done today, but people talk about as a way of cleaning fossil fuels. There's a lot of controversy behind CCS, sequestration, right now, but the main idea of how this works is you combust all the material, and then instead of emitting CO2 into the atmosphere, is you chemically react CO2 with some sorbent, and you store it away into like salt beds, and you can actually just replace the fuel that you're taking out for like in like oil and gas reservoir. You extract the oil, you extract the gas, and you replace it with CO2 into or into like salt beds, and essentially you're taking the CO2 and you're just shoving it underground, so it doesn't go into the atmosphere and it doesn't lead to the effects of global warming and climate change. There's a lot of research being done on this. Currently, it's not implemented. It's actually really expensive, and even from a technical side, I think that it still has a bit to go in order to be able to be implemented at scale. And so there's a lot of active research currently in the area. But besides that, there's also, it would require construction of new infrastructure and so on and so forth. And this is kind of a rough map to give a sense of where we could potentially do sequestration and store it away. And so CCS for carbon capture and sequestration. Once you combust it, taking the CO2, shoving it underground. That's the idea here. And so people point to this as a possible way of making fossil fuels clean. It doesn't get around the issue of the resource adequacy and availability, which we talked about earlier in today's lecture, but it is one way of thinking about doing climate change. And a lot of folks who think that we can't get away from fossil fuels point to this as the solution for still being able to meet climate change goals. Okay, great. Sorry, I'm a little bit over today. Look forward to having the project descriptions posted online later today, and then make sure to review those materials and to fill out the Google Forms by the end of the week. Thanks, everyone. I'll stay on for another quick minute if anyone has any questions.